Hi everyone. So you may be familiar with Pascal's triangle, one of the most beautiful objects of all of mathematics. Pascal's triangle is well known for being useful in algebra class, especially for binomial expansions. Today, I'm going to show you that while it's useful for your algebra classes, it's also useful for your calculus classes as well. Let's get started. So let's begin by answering, what is Pascal's triangle? Well, Pascal's triangle is in front of us right now. Let me show you how it works. So what we do is we can start with this first row right over here, and let's examine it. We see a 1 in the center, and then there are zeros going to the right of that 1 and to the left of that 1, infinitely to the right and to the left. And then what we want to do is we want to take each of the digits, each pair, and add them together and write the sum below that pair. So for example, we can take 1 and 0 and add them together to produce 1, which we write underneath. And another example is we take 0 and 0 and we add it together to produce 0 underneath. And so by doing that process, we generate an entire new row of numbers. This row right over here. And then we repeat that process again. We take each pair of numbers and add them together and then write the sum below the pair of numbers. We take 1 plus 1 is 2. We take 0 plus 0 is 0. And so we get another row. And we keep doing that. We get another row, we get another row, and we get another row, and this goes on infinitely forever. And so we get a triangle in the center. I mentioned that Pascal's triangle is useful in your algebra classes. How so? Well, Pascal's triangle is useful for expanding binomials raised to some power. In particular, it's useful for expanding polynomials of the form x plus 1 to some power n, where n is some natural number which includes numbers such as 0, 1, 2, 3, and etc. So let's do an example. Let's first do it the manual way. Here we start with x plus 1 to the third power. And in order to expand it, it's an entire process. We first have to multiply x plus 1 by itself 3 times here. And then we can combine the first two terms. And then we can combine all the terms. And we get this expression down over here. Now, looking at the expression at the bottom, we can actually see that there's an implicit 1 here, and there's an implicit x to the 0 power right over here. Now, let's take a look at the coefficients. We see 1, 3, 3, 1. If we look up here, we actually see 1, 3, 3, 1. So that's pretty cool. We can see that this row correlates with x plus 1 to the third. The third row of Pascal's triangle, where the 0th row is this row right over here, corresponds with x plus 1 to the third. And we can continue that by saying the 0th row corresponds with x plus 1 to the 0. And the first row corresponds to x plus 1 to the first, and so on. X plus 1 to the second, x plus 1 to the fourth, x plus 1 to the fifth. And so just to do an example, to see how we save time, well, x plus 1 to the fifth, it would be really hard to expand that as we did down here. So what we can do is do it the easy way. to expand x plus 1 to the fifth, let's just write out all the numbers that are here. We can write 1, 1, 5, 10, 10, 5, and 1. And we just write x in increasing powers. X to the 0, x to the 1, x to the 2, x to the 3, x to the 4, and x to the 5. And put plus signs in between. And there we go. We expanded x plus 1 to the fifth. So Pascal's triangle is very handy. Now let's move on to the crux of our video. Why is Pascal's triangle helpful for calculus? Well, in order to understand this, we need to understand power series. So this is the general form of a power series. Now, it is a series, meaning it's a summation of infinite terms, and each of these terms has a constant and a variable subtracted by a constant raised to some power that's increasing due to the summation. When we expand this out, we get a constant, and we get a variable subtracted by a constant, and we get increasing powers. So let's see a specific power series. So we can set all of the c constants, c0, c1, c2, all of them to 1, and we can set a to be 0. That leaves us with this particular power series. Now this power series has an interval of convergence. And this interval of convergence is -1 to 1. Now let's understand this notation a little bit. So -1 to 1, with these parentheses, what that means is the set of all real numbers from -1 to 1, but not including -1 and 1. The parentheses indicates not including. If you have a bracket, however, now the bracket means that it's including the -1 in the set. So our interval of convergence is -1 to 1, but not including -1 and 1. So what does this mean? Well, it's important to understand what converge means. Converge simply means that when you have a series, and when that series converges for a particular value, what that means is that as you add more and more terms to the series, that series approaches a particular value. So in our interval of convergence, since it's -1 to 1, but not including -1 and 1, that means that if we were to choose any value in this interval of convergence, our series will converge or approach a particular value as we increase the terms. Any value outside of our interval of convergence, such as 1, -1, 50, -50, 100, -100, all of those values will cause our series to diverge. And diverge basically means that as you add more and more terms, it's not going to approach a specific value, and instead will approach infinity, -infinity, or it won't approach a particular value at all. Maybe it hops between 0 and 1, for example. So let's choose a particular value from our interval of convergence. For example, 1/2. And we've illustrated that below. So we've added 1/2, and we get 1/2 to the 0 power, 1/2 to the first power, second power, third power, fourth power, etc. Now I say this sums to 2. And how can we understand this? Well, we can actually do so with a geometric picture. So we'll start by describing the interval from 0 to 2. And we're going to actually put the sum on this interval as we add more and more terms. So we start with the first term, which is just 1. And so we write that on our number line. We go to 1. And then we add 1/2. So we then go up by 1/2. And you can see basically we're taking our distance from 1 to 2 and halving it. And then we add 1/4. So basically we have our distance, and what we're doing is we're halving it because we're adding by 1/4. And then we add 1/8. So we have our distance, and we're halving it. So we're getting closer and closer and closer to 2 by halving our distance from 2 each time with another term. And hopefully it's pretty clear that this sum gets closer and closer to 2, and for that reason we say it converges to 2 and that the series is equal to 2. In our calculus classes, one problem that we're often told to solve is to find the power series representation of different functions. So for example, this question right over here is pretty common. Find the power series representation of 1 over 1 plus x to the third power. Now, surprisingly, this problem can be easily solved with Pascal's triangle. But let's do it the calculus way, the way that you were taught in school. So we often start off with this particular fact. This fact says that 1 over 1 minus x is equal to the summation of n is equal to 0 to infinity of x to the n over the interval of convergence minus 1 to 1. In particular, what this is saying is that when x is between -1 and 1, the interval of convergence, then this series converges. And the value it converges to is expressed by this function. So this is spelled out in detail down below. Now, what we want to do is we want to try to get close and close to 1 plus x over 3. Now, to do that, let's try to get 1 over 1 plus x by itself. Not to the third, not to the second, but just to the first power. So to do that, we can do the following. Let's substitute, in place of x, let's actually substitute minus x. I can do a little bit of cleanup here. So if we substitute minus x here, then we'll have to substitute minus x here as well, as we do here. And we'll also have to substitute minus x here, like we do here. And now we can then simplify. We get from here, we can simplify to this, which is what we want. And we can take out the -1 from the x, negative x term. And we can also divide by -1 to get this. Simplifying even further, well, we can write this as a negative exponent. This stays the same. And we can just write this as an interval of convergence. And you can see that the interval of convergence is actually the same as it was up here. All right, so let's keep going. Now, we need to know an important property of differentiation. So if you have a power series, like here, and you differentiate both sides, now the interval of convergence may change. So if the interval of convergence was something like this, Let's say it was -5 to 5. Whenever differentiation happens, the interval of convergence is still going to be from the same numbers. So it's still going to be from -5 to 5. It's still going to take up the same distance. But the thing that could change is that endpoints could be lost. For example, this interval contains -5. It may stop containing -5, or may stop containing 5. But that's not necessarily the case. When you differentiate, the endpoints could still be retained. In order to figure that out, you have to perform particular tests. Now, we're actually lucky in this case, because our interval doesn't actually contain any endpoints. So when we differentiate it, there's no endpoints to lose. So we can be confident when we're differentiating that our interval of convergence stays the same. So we're lucky in that aspect. So let's continue. Now let's differentiate, because when we differentiate, we can hopefully get an expression for not just 1 over 1 plus x, but also 1 over 1 plus x squared and 1 over 1 plus x cubed. So differentiation should help with that. So here we go. We've differentiated both sides, and our interval of convergence stays the same because there's no endpoints to lose. And doing the differentiation, we get this, and we get this, and our interval of convergence stays the same. So that's great progress. Now let's differentiate again. Again, there's no endpoints to lose, so the interval of convergence will stay the same. We differentiate, same interval of convergence, and solving for the differentiation, we get this, we get this, and we get this interval of convergence. And now all we do is we bring the 2 over here and we just divide by it to get our answer. 1 over 1 plus x to the third can be expressed with this expression and with this interval of convergence. So that's great. We solved our problem. Now let's take a look here. Now this series right over here, we can actually start writing out some of the terms. So this expression, when we write out the terms, we get 1, 3, 6, 10, 15, and etc. So this is pretty interesting. Let's see how we can make use of this. So I wrote the series we were focusing on down here. And I also wrote Pascal's triangle up here. And I also wrote the finding we made about the rows of Pascal's triangle. In particular, that when you expand x plus 1 to the 0, x plus 1 to the first, x plus 1 to the second, that just corresponds with the rows of Pascal's triangle. In particular, the coefficients are on Pascal's triangle. So now let's focus on the coefficients in the bottom series. 1, 3, 6, 10, 15. Are they in Pascal's triangle? Well, yeah, they're here. 3, 6, 10, 15, and if we continue this series, we'll see 21 as well. So this is quite interesting. We can see that the third diagonal of Pascal's triangle, where this is the first diagonal of Pascal's triangle, that corresponds with 1 plus x to the negative third. And this actually continues. This corresponds with 1 plus x to the negative second. And this is 1 plus x to the negative first. And this is 1 plus x to the negative fourth. This is 1 plus x to the negative fifth, and etc. In particular, the correspondence is regarding the power series coefficients. So, if we were to remove this down below, we could use Pascal's triangle in order to find the power series for this function. We can use Pascal's triangle. We see a 1, we see a 3, 6, 10, 15, and we can leave that for now. And we can write x with increasing powers, x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, and we just need alternating signs. Positive, negative, positive, negative, positive, negative. And we could do a little dot, dot, dot. And there we go. We found the power series representation of the function a lot quicker. Very, very handy. And just to drive home the process, let me do one more example. Let's write the power series for 1 plus x to the negative fifth power. Well, this can be done using the fifth diagonal of Pascal's triangle. So we have 1, 5, 15, 35. So we can write 1, 5, 15, and 35. And we can write x to the 0, x to the 1, x to the 2, x to the 3, and then we can alternate the signs. We have positive, negative, positive, negative, positive, and etc. And by the way, the interval of convergence for all of these will always be -1, 2, 1. Now, what I find so cool about this is the rows of Pascal's triangle help us find x plus 1 raised to either a positive number or 0. And we can find the coefficients of that expansion. The diagonals help us find the coefficients of the power series expansion of x plus 1 to the negative power. X plus 1 to the negative 2, x plus 1 to the negative 3. So it's a pretty fascinating relationship between the rows and the diagonals. So I hope you had fun watching this video, and I also hope you learned something new. This video was a lot of fun to make, and this concept was really fun to explore. When I realized this while looking at Pascal's triangle, I found this concept to be pretty mind-blowing. So please let me know what you thought of this in the comments, and thank you so much for watching. Have a nice day.